Okay, so as promised, last time we talked about recursion, and we looked at recursion through an example of the factorial function. So so recursion is when a function calls itself from within itself. So for example, a bunch of people are joining. Remember, if you log into Zoom with your Concordia credentials, you won't get put in a waiting room. It'll let you right in. All right, so recursion is when a function calls itself from within itself. So for example, factorial is a good simple example to think about recursion with, where 4 factorial is, we can think about it iteratively and say, well, it's 4 times 3 times 2 times 1, which gives us a 24. But really, 4 factorial is equal to 4 times whatever 3 factorial is. So that's it calling itself recursively. While we're calculating 4 factorial, we use the factorial function again to figure out 3 factorial. And 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. 1 factorial is 1. So this is where the recursion ends. And then after we have this answer, we can answer this one, which lets this guy finish. We can answer this one, which lets this guy finish. Then we can answer this one, which lets this guy finish, which then gives us our final answer. All right, so we're learning about recursion. We look at a simple example first, and then we look at an example that is going to give you nightmares. So we're going to talk about merge sort today. So merge sort is what's called a divide and conquer sorting algorithm. And I mentioned last time that recursion is very memory inefficient, because every single time we need to pause a call to a function while we wait for the next recursive call to give us our answer, that gets thrown on top of something called a stack, the computer stack, where we have to remember the current state of all the variables and things like that. So we would say that recursive calls are memory inefficient, but sometimes the algorithms themselves can look very elegant. So somewhere in there, we have to make that decision between the resources available on our computer, speed of our computer, and the kind of data we're working with. So for instance, you may not use merge sort on a single computer if you're sorting 1 billion things, because that's going to be a lot of calls to merge sort, which is going to lead you to run out of memory. So even though we might say merge sort in and of itself is a more efficient approach to sorting data, the amount of data, the memory it's going to use is great. So we might say, well, why ever use merge sort if computers are really, really, really fast, and even less efficient sorting algorithms like insertion sort or bubble sort are, let's call it, good enough. The reality is merge sort is compatible with parallel processing. All right, so when you think about our computers today, we're usually not dealing with single core computers. We're dealing with dual core, quad core, 8 core computers, even more in some cases. And then on top of that, we have libraries and infrastructure available in the cloud that allows us to split workloads across multiple computers. So if you have 1 billion things you need to sort with merge sort, you can actually sort that very, very, very quickly by dividing up the work among a whole bunch of different computers, and each of those computers' resources is working on their little piece of the pie. Okay. And I think I used an example in class last time about like shoveling snow, which is appropriate for today as I look out my window and see the snow coming down. If we had 5 people working on shoveling a parking lot, it's going to get done a lot quicker than if you had 1 person trying to shovel the parking lot, even if that 1 person was a faster shoveler or something along those lines. Okay. So merge sort is very compatible with parallel processing, which gives us a reason to use it sometimes. Typically, there is a little twist on merge sort that is commonly used when you have a programming language that has a built-in sort function. It probably uses a sort called quick sort, which is very, very, very similar to merge sort. All right, so Having said that, let's look at merge sort as an example. And this is where I get to draw some of my pictures. And remember, I'm an expert at that. All right. Where's my shapes? Go. So I'm going to give myself a list of 5 numbers. I'm purposely doing 5 here instead of 4, because it'll help you visualize how do we divide something in half when you have an uneven number of things, because we're going to have to write the algorithm generically to deal with the first half and the second half. All right, I'm going to fill this guy up with just random numbers, purposely having them unsorted. All right. And for the sake of our example here, we're going to call this array AR. All right. So now I'm going to go back a slide here and add another bullet point. We're going to say that merge sort is built on top of the premise that a list with exactly one element in it is trivially sorted. All right. So if I give you a playing card, I gave you a single card, I asked you, is the collection of cards in your hand sorted? You would look down, you'd giggle a little bit and say, of course it's sorted. You only gave me one card. So we're going to say a list with exactly one thing in it is trivially sorted. That's going to be the piece. That's going to be kind of the equivalent to what we ran into here at the bottom of the factorial for recursion, when we finally hit this thing where we stopped calling things recursively and we started bouncing back up and doing some stuff. Okay. So we have our original list here. We're going to ask the question, is this list of 5 elements, and actually let me just go ahead and index them here. I'll make these guys different color. All right, so the 3 is at bucket 0, the 1 is at bucket 1, the 7 is at bucket 2, the 5 is at bucket 3, the 2 is at bucket 4. Okay, so this is our list, or our array of integers in this case. All right, so we're going to ask ourselves, is this list trivially sorted? The answer is no. I see 5 things there, and by definition, 5 things is not trivially sorted. Now, I'm really trying to drive that point home about it being trivially sorted, because as a human being, we might glance at this, and in this case, it's not, but it's possible that the 5 numbers could be in order. But from a merge sort perspective, if you're looking at 5 numbers here, it's not going to look at the actual numbers and whether or not they're in order. It's going to just look at, am I trying to look at more than one number? If I'm looking at more than one number, it is not trivially sorted. Okay. So in this case, I'm looking at 5 numbers. Now, I'm going to put a couple of other things in here that we're going to keep track of. So we're going to keep track of a position called begin and a position called end. So we might say here that, okay, this list is not a one list because begin and end are different numbers. Okay. So this guy has a length of 5, but you can't operate off the length of the array, because what we're going to be doing as we make calls to merge sort, we're going to be passing a pointer to this array around. So every single call to merge sort will technically have access to the entire array, but they're going to be told what portion of the array that particular call of merge sort is in charge of looking at. All right. So if I'm a single call to merge sort, in order for me to tell whether or not my my part of that array is sorted, I have to say, is begin and end, are they the same number? If they are, I'm looking at a one list, it's sorted. If not, so in this case, begin is 0, end is 4, it's not sorted. What am I going to do? I'm going to call merge sort twice. So we're going to call merge sort on the array from bucket 0 to bucket 1 inclusive. We'll figure out how to get these numbers soon. So I'm going to send it that part. And then we're going to call merge sort, passing it bucket 2 to bucket 4. And actually, just to make the math work correctly the way you're going to end up doing it, I'm going to actually make the second half the larger half. And you'll see why when we look at, well, I'll just tell you now. How do we figure out the first half of the array, the beginning and ending of the first half versus the beginning and ending of the second half? Well, some people will say, oh, well, isn't it just end minus begin divided by 2? Well, actually, you probably wouldn't say that. You would say the length. No, you would say end minus begin divided by 2. And that works when we're dealing with the front of the array here. But let's say that we were in a place here where we were looking at begin is 3 and end is 4. 4 minus 3 is 1. 1 divided by 2 is 0. So now the new begin is here. That's the left half. You see how that math doesn't actually work? So what we would actually do is say end plus begin, which is 7, divided by 2 is 3. That's going to be the beginning of your first half. All right, so the math we use to divide up our merge sort changes. So if I want the left half here, I'm going to say left half starts at position begin. So begin is 0. Again, I've decided this list right here is not trivially sorted because it has more than one thing. Begin and end are not equal to each other. So I'm going to have to call merge sort on the left half and call merge sort on the right half. So I'm going to tell merge sort, here's the entire array. Here's the beginning and ending, and I include the end in my example here. So end is equal to 4, which is the last legal position in the array. All right, so the left half of this guy is wherever begin currently is, all the way up to, in this case, bucket 2. How did we get the bucket 2? 4 plus 0 divided by 2 is 2. All right, now pay attention to that piece there because that's a common error point with merge sort, is how do you figure out where your halves are? And the reason it's common is you could say, well, what isn't it just n divided by 2? Well, that works in this case, but if you're at a different point in the array, the math won't come out right. So you really need to work with begin and end to find out the middle point. So that is begin plus n divided by 2. I'll put a little comment over here. Begin plus end divided by 2. That's how we get this 2 here. And then how do we get this 3? It's 1 plus that. So once we find the end of the first list, the beginning of the second half is 1 plus that number, all the way up to whatever end currently is. All right, so I'm going to steal this slide. We're actually going to I'm going to steal it twice, but we're going to make our first call to merge sort here. So I'm making a call to merge sort here and another call to merge sort. This second call will not happen until this first call to merge sort has completely finished. So it's going to be dealing with the left half of this list for a little bit. before it finally bounces back. And this call to merge sort finishes so that the second call, the second original call to merge sort can continue. All right, so I'm calling merge sort on this guy right here. So that's my call to, and sorry, this should be begin. All right, so this is my call to merge sort, passing it the entire array, and the position of the array is begin to end, like that. So even though I have access to these buckets over here, I'm not interested in those buckets. So then we ask ourselves, if begin is equal to end. It's not, so this is not a one list. I'll go ahead and put that on this first thing too, so you have access to this for when you go to write this. All right, so this first time through, begin is not equal to end, so we call merge sort twice. Once for the first half, once for the second half. Here's the call to the first half. Is begin equal to end? It's not. Begin is 0, end is 2. They're not the same, so we call merge sort twice. We call it on the array from bucket begin to bucket. So instead of 2, it's going to be begin plus end. So 0 plus 2 is 2. Divided by 2 is 1. So this would be the first half. Hold on, I want to do something here real quick. 4 plus 0 is 2. 2 divided by 2, or 4 divided by 2 is 2. Okay, we're good. Just got to make sure you're consistent on how you're finding your midpoint. All right, so my first call to merge sort here will be the entire array, but from bucket 0 to bucket 1. This would be the left half. And then for the right half, it'll be 1 greater than that, which is 2, all the way to what end currently is, which is 2. All right, so already we can see that when we finally get to the second call of merge sort here, that's going to be a trivially sorted list. So if I'm looking at this array AR from bucket 2 to bucket 2, this 7 in and of itself is in order. I don't have to do anything magical to a list of one element to make it sorted. All right, that's this concept that merge sort is based on. All right, but we're going to call merge sort on this piece here. Paste that in. All right, so here's my merge sort on 0 to 1. So that's begin to end is there. And then what I can also do here is I'm kind of building my stack here. Oh, a second. This guy. So that's my first call. And this is my second call. I haven't gotten to the second call yet. But because there were 2 calls, I went ahead and copied the slides. All right. So I'm looking at the situation where begin is 0, end is 1. Is begin and end the same? It is not. So what do? I call merge sort on the left half. I call merge sort on the right half. The left half will be from begin, bucket 0, to begin plus end. 0 plus 1 is 1. Divided by 2 is 0. So that'll be the left half. And then I'll call it on that 0 plus 1 all the way up to wherever end is, which is 1. So those are my 2 calls to merge sort. my next two calls to merge sort. Paste that, paste that. All right, so here was that first call. So now I'm in a position where begin is 0 and end is 0. Are they the same? They are. So I do not call merge sort in this case. We're just going to say array is trivially sorted between 0 and 0 because we're looking at a one list. What does that mean? It means do nothing. If merge sort's job is to sort its little section of the array, and this particular call to merge sort was handed a section with exactly one element in it, it can just say, my work is done, easy peasy, move on with life. All right. So this guy then ends, so he can bounce off. He's removed from the stack, which then gets me to my second call to merge sort here. So this guy just finished. He was put onto the stack. We determined it's a one list. It was trivially sorted. So we bounce back from that. Now we can make this second call, which is from 1 to 1, is begin and end. Let me just shift my begin and end here. Are begin and end the same number? Is 1 equal to 1? Yes, it is. Should have saved my, so this is trivially sorted. Do nothing. Okay. So this call then ends, leaving us right here. After both calls to merge sort finish, we do the merge step. Okay, so let's look at the merge step. I'm going to steal this slide. So now we're going to say, now merge the two halves together. So we know that the left half from bucket 0 to bucket 0 is sorted. And we know the right half from bucket 1 to bucket 1 is sorted because we called merge sort on those two halves and they both bounced back. So we know that this guy is sorted. We also know that this guy is sorted. We also happen to know that we haven't done anything at this point. They just happen to be sorted because they're one lists. So now what we need to do, and what I'm going to do here is I'm going to give you some hints for variables. So this is begin 1 and end 1. I'll just stack them. This is begin 2 and end 2. Okay, so at any particular call to merge sort, you're figuring out where the beginning and ending of the left half is and where the beginning and ending of the right half is. You're going to keep track of those 4 positions. All right, so really when we called merge sort right here, we passed it begin 1 and we passed it end 1. We passed this guy begin 2 and we passed him end 2. The numbers I had there were correct. So if you go back and watch this video and pause it, you'll see the correct numbers. But ultimately, what I would have done in code is I would have set begin one equal to a value, end one equal to a value, and then done the math of begin one plus end two divided by 3 equals end one, or divided by 2 rather equals end one. And then 1 plus that is my begin two. All right. So now I effectively have 2 halves of my list. This particular call to merge sort, my entire world lives right there. All the stuff over here, even though I have access to it, that's going to be somebody else's job to deal with those numbers. Some other call to merge sort. It'll be their job to deal with those numbers. All right. So this call to merge sort's dealing with just that section of AR. And I'm merging together this sorted list and this sorted list. That's what I'm about to do, is that merge step right there. All right. So how do we do the merge step? Well, we're going to keep track of the position that we are in each of these lists. So I'm going to add another variable. We're going to call this guy pause1. We're going to call this guy pause2. All right. Now we know that we have a total of 2 things that we need to place. So I'm going to create a temporary array here. So a temporary 2-bucket array to hold my, I'm going to call them winners. All right. And then what I'm going to do is I'm going to start walking through the elements of my list, finding out which number is smaller, the number at position pause1 or the number at position pause2. All right. So first time through, I asked the question. Pause1 is currently a 0. Pause2 is currently a 1. So is the value that lives at bucket 0, which is a 3, is that guy less than a 1? It's not. So 1 is my smallest number. So I'll go ahead and put a 1 there, and then I'll increment pause2. Now pause2 just ran off the end of my list. Okay. So now the next time I ask the question, I say, is the value at position pause1 right here, is that less than the value at pause2, which is currently at an illegal position? It's illegal because pause2 is greater than n2. So this guy right here, he's not in play. I can't compare him to anything because my whole world in this call to merge sort is that piece right there. So really what I'm asking here is a 3 less than illegal value. So the answer is 3 wins against no opponent. All right, so I'll place my 3. Then I'll increment pause1. Pause1 is now greater than n1. Pause2 is now greater than n2. So we've now placed all of our values. All right. Now what we'll do is we will copy over this 1 and 3, overwriting the portion of this array we were dealing with. Okay, because this was just a temporary array right here. So in the original array, remember we're passing around a pointer here. In the original array, I've now updated it to have 1 and 3. So this little section of the array that this merge sort was in charge of is now sorted. The whole array is not sorted yet, but this one little section is sorted, and that's what this guy's job was. So I'm going to steal that there real quick, because I'm going to, when I bounce back up, remember, we just finished this call. Which means at this point, my array looks like that. Because again, I'm passing around a pointer to AR. So when I made a change to my array here, that change was felt everywhere. Everywhere that has access to AR now has its values updated in that one little subsection. Okay. So now our call to merge sort, this particular call to merge sort is now done. Okay. So that is this guy right here. We bounce back up. This call to merge sort's finished. So now we call merge sort on AR22, which is this guy right here. Is begin and end the same? It is. So we're trivially sorted already. We don't need to do anything special. So we'll bounce back up. Now what do? We do our merge step, where we have begin 1, end 1, begin 2, end 2, and then I'll create my other variables. Pause 1 starts off at wherever begin 1 is. Pause 2 starts off wherever begin 2 was. I remember this call to merge sort. I'm dealing with exactly that portion of my array. Notice that the left half is sorted in and of itself. So 1 is less than 3. I've already sorted that portion of this array. And my right half is sorted in and of itself. It didn't take much work because 7 was already sorted. So now I'm going to do my merge step. I'm going to create a temporary array. That's the same size as this array up here. I'm going to say, which is smaller, the value at pos 1 or the value at pos 2? 1 is less than a 7. So I'll place the 1. I'll increment pos 1. Which is smaller, the value at pos 1, which is a 3, or the value at pos 2? The 3 is smaller. So I'll place my 3. I'll increment pos 1. Which is smaller? Now notice that pos 1, and sorry, this end 1 should be right here. Notice that pos 1 has now gone off the end of the left half because it's greater than end 1. So really what I'm asking here is which is smaller, an illegal value or a 7? So 7 is running a race against nobody. So he wins. We increment pos 2. Now both pos 1's off the end of his half, so it's greater than end 1. Pos 2 is off the end of his half, because it's greater than end 2. And now I have this portion of my list sorted. It just happened to already be sorted. So I'll go through the motion of copying the 1 back over. I'm copying the 1, 3, and the 7 back over from my temporary array to the original array here. So this is what my original array now looks like. And everybody who has access to this guy has this updated version because I'm just passing the pointer around. All right. So now this call to merge sort, the original call to merge sort on the left-hand side has now finished. So now I just finished my original first call to merge sort, which was the left half of my original list. And we see that the numbers on the left half are now sorted. All right, so now we're going to call our second call to merge sort, 3 to 4. All right. So that is begin and end like that. Are begin and end the same number? They are not. So I'm going to call merge sort on the left half, which will be from begin, which is 3, to begin plus end. So 4 plus 3 is 7. 7 divided by 2 is 3. Very, very, very important. How do I get the end of the first list? End 1 is equal to begin plus end divided by 2. This is going to save you when you do your homework a lot of time. That is the math to determine the end of the first half. Because you might be tempted to just say, oh, well, isn't the end of the first half just whatever end is divided by 2? That guy actually starts before the beginning of my left list. So the math to get N1, this is N1 right here, is begin plus end divided by 2. This is the magic of merge sort. This is the difficulty of merge sort, is that stupid little equation there. Okay? And then I'm going to go, my second call to merge sort will be whatever that number is, plus 1, all the way to whatever end was. All right, so I'm going to make a call to merge sort for this guy. And another call for the other half. I'm making 2 calls to merge sort. But remember, the second call will not even start until the first call has finished. So I call my merge sort on 3, 3. Begin and end are both 3. Is begin and end equal to each other? Yes, it is. So that means this portion of the list, this is what this call to merge sort's looking at, just that single element is already sorted in and of itself. So I don't need to do any magic. I don't do the merge step. I just say, I'm done. So this call to merge sort ends. Which then allows, so this guy just finished. So now I'm able to make my second call to merge sort, which is this guy right here, where begin and end are both 4. Similar situation, begin and end are the same, so I don't need to do anything special. This call to merge sort is done. So now I bounce back up to this level. I do my merge step. I know my left half is sorted in and of itself. I know my right half is sorted in and of itself. So I'm going to, just to keep things consistent here, I'm going to say this is begin 1, this is end 1. This is begin 2. This is end 2. This is pause 1. This is pause 2. I'm going to make a temporary array. Now, when you go to do your homework, you're definitely going to want to walk through this video and listen to the words I'm saying, because I'm effectively telling you the code. I'm just not writing the code in front of you. All right. So I create a temporary array capable of holding 2 elements. But now, so pay extra attention here. When I make a 2-bucket array, it's going to be indexed 0 to 1. Even though I'm going to be sorting the things from buckets 3 and 4 in my original array. I need to make sure I account for that when I go and copy the values back over. So then I ask the question, is the value at pause 1, which is 5, is that less than the value at pause 2? It's not. So pause 2 was my winner. I record that. I increment pause 1, or I'm sorry, I increment pause 2. Then I ask, is the value at pause 1 less than an illegal value? It wins by default. I place my 5, increment pause 1. So now pause 1 and pause 2 are both off the ends of their respective halves. We are done. So now I need to copy this 2 and 5 over the section of my array between begin 1 and end 2. So when you go to copy the values back, even though I'm copying bucket 0 here, I'm copying it at position begin 1, which is 3. I'm copying bucket 1, I'm copying that at position end 2. Okay, so just make sure when you go and copy this stuff back, you're putting it into the correct place in your original array. even though your temporary array would be indexed from bucket 0 to bucket 1. So you might need two counters, one to walk through your 0 indexed array, and then another one that keeps track of where you are in your original array. Hint, hint. Okay. So now we copy over the 2 and the 5. And now this call to merge sort is complete. So now we're back to our original call to merge sort. Notice the left half is sorted in and of itself. The right half is sorted in and of itself. So now I'm going to do my merge step. Just to stay consistent, this is begin 1. This is end 1. This is begin 2. This is end 2. This is pause 1. This is pause 2. We make our temporary array, which is the same size as the original array. And then we start asking our question. Is the value at pause 1, which is a 1, is that less than the value at pause 2, which is a 7? Yes, it is. I record the 1. I increment pause 1. Next, is the value at pause 1, which is now a 3, less than the value at pause 2, which is a 7? Yes, it is. I'm sorry, 137. I put my pause 2 in the wrong place there. Let me just back up for a second. I put it at end 1 instead of begin 2. So roll back 15 seconds. I'm comparing my left half of my list right here to my right half of my list, where pause 1 and pause 2 begin at the first element of each of those lists. So I ask myself, is the value at pause 1, which is a 1, is that less than the value at pause 2, which is a 2? Yes, it is. I record the 1. I increment pause 1. Is the value at pause 1, which is a 3, is that less than the value at pause 2, which is a 2? It's not. So I record pause 2 as the winner. Increment pause 2. Is the value at pause 1, which is 3, less than the value at pause 2, which is 5? Yes, it is. Record the 3. Increment pause 1. Is the value at pause 1, which is 7, less than the value at pause 2, which is 5? No, it's not. So pause 2 is the winner. Increment pause 2. Is the value at pause 1, which is a 7, less than the value at pause 2, which is illegal? It wins by default. So there's my 7. Increment pause 1. We're done because pause 1 is off the end of its list because it's greater than N1. Pause 2 is off the end of its list because it's greater than N2. And now what I do is I copy my elements back over the original array. And there is my sorted array. That's my very last call to merge sort. Just it's my original single call to merge sort. So if we want to think about what this original call was, it was to get the ball rolling here. It was merge sort, passing it AR, passing it 0 for the begin, and passing it 4 for the end. I got this whole sort going by calling merge sort on my array from the first element all the way up to the last element, including the last element. Okay, so questions about how merge sort works. So now what I'm going to give you here in your last couple minutes is I'm going to give you an array with some random integers in it. Right, we're going to be dealing with Java here. And we can do all this just inside of main. We don't need a separate class here. I am going to need a library called java.util.random. I'm going to say int array AR is equal to a new int array. Let's just put 11 elements in it. Now I'm going to go ahead and give myself a function called display that takes an int array as a parameter. And it's going to go through and just display all the elements in that array just so we can test this. So int I is equal to 0, I is less than ar.length, I plus plus. I'll do a system.out.print. I'm just going to do a print. That way it puts them all in the same line. And I'll say AR at bucket I concatenate with, I'll just put a space between the numbers. And then at the very end, I'll just kick it down a line. So now I have a function that I can pass any integer array to, and it'll spit it out to the screen so I can see it. All right. Now what I'm going to do is I'm going to go ahead and fill my array up with random numbers. So I'm going to say random R is equal to new random. Rent I is equal to 0. I is less than AR dot length. I plus plus. AR at bucket I is equal to R dot next int. Yay. And now that's going to give me a value in the range of all integers. So that'll be negative 2.1 billion to positive 2.1 billion. I'm going to go ahead and mod this guy by 50, which will give me a number between 0 and 49. Okay, and then I'll call display, and I like to use the name of the class. So I'll say main dot display, passing it AR. Go ahead and run that. I should have my 11 random integers. Oh, I've got some negative numbers in there, so give me a moment. I guess it's technically not a problem, but I'll show you the function to get the absolute value. There's a math library that has a static, so this is a class called math. There's a static method called ABS, absolute value, that I'm passing this number to, and it's giving me the absolute value of those numbers. So for your homework, static void merge sort int array AR int begin int end. And I'll go ahead and make the initial call. So your initial call to merge sort will pass it the entire array, the very first legal bucket, the very last legal bucket, including it. This follows our the example I did in on the slides. So your homework is to write merge sort such that write merge sort as we did in class on 1/12/24. Say see video. All right. Any questions on what I'm asking you to do? And this will be due on Wednesday since we do not have class on Monday. Um, I strongly encourage you to walk through the slides slowly to make sure you fully understand it. I promise you this is not nearly as hard as it seems, but it will be an assignment that will stress many of you out, and that's common. Okay, I promise by the time you're seniors, this will seem way easier, but it's an important thing. It's like almost a rite of passage you have to go through right now. Okay, so make sure you're using Slack to ask any questions. I put up a new thing for the spring this class, so that's up on Slack, and I will put the assignment and make sure I upload the video here right after class. Sound good? And hopefully I made a reasonable amount of sense and wasn't stumbling over my words. In my head, it sounded good. Is that an accurate statement? Yeah, we got nothing.
Yeah, sounded good.
Everybody's sleeping. I find out I never even opened Zoom. I've just been sitting here talking to myself for an hour. All right. Well, I will see everybody on Wednesday. Just as a heads up, next Friday we'll have to do the same thing because I have the left half of my back is getting the surgery done next Friday, but presumably I'll be able to think clearly enough to do a Zoom lecture. So that's the plan for next Friday as well. But Wednesday we'll be back in person. All right.
Sounds good, Professor.
All right. Be safe out there if you are driving because there's a lot of crazy snow. You guys take care.
Good long winter weekend.
All right. Take care.
Mhm.